Good morning. Testing audio. Testing audio. Okay. Okay, fine. Okay, good morning, everyone. Good morning, and thanks everyone for being here. First of all, it's a pleasure to be in the University of Florence, where I also have the chance to come. Thanks to collaboration of many years now, for also teaching some of the students of this university on hydraulics. So it's a pleasure to be here. Thanks for the colleagues at the University of Florence that are supporting us to have this room that is not easy in COVID times. Okay. So welcome to we named this digital mapping courses. The 2021 edition is Geospatial Intelligence for mapping land and water change. You already received some preliminary information, you know why you're here. I hope you give a look at the website. We're going to use geospatial technology, the Google Earth Engine platform, just to give you right away some motivation to go while you're here. So, my name is Fernando Nardi. I'm an associate professor of hydrology at the University of Foreigners of Perugia, where since 2017 I'm on duty as director of the WaterDoc. It's a multidisciplinary research center. Just introducing you like the background and motivation, multidisciplinarity. The digital mapping with its general name started in 2017 with the goal of teaching any student. We have a lot of humanities students, so it was an easy start to do mapping in, originally was 3 days, then 2 days, and then with the team, we designed tutorials so that anyone can start mapping using web technologies. Earth Engine is a science platform, more advanced, requiring programming, but the spirit is the same. In 8 hours or less, you will be able to code and do the map. And we are confident, we got ready, even this course was organized in the last 2 weeks, that you will be able to do so. I hope also the online participants are hearing me. Let us know if this is not the case. Let me give you just, 2 minutes of introduction of the organization. First of all, without naming all, but this event is organized within the Earth Technology Expo. It is a conference that you will be joining this afternoon. Because of COVID and logistics, we decided to have the technical session this morning. So we have tables, room, Wi-Fi, and everything this morning. So the organization is the entire morning here, lunch break free on your own, and then we move to Fortezza. I hope that now most of you living in Florence, you know how to get around. We will give you enough time for having lunch and moving the other side. So from now to 1:30 p.m. here, and then we will be at Fortezza, the conference starting 3 p.m. So the morning you will do the training, you will do also a project that we will do, together with our tutors, and you organize probably in groups. And then in the afternoon, you will complete the project, prepare a presentation, and present it. There will be also a challenge for you. And the conference, it will be people, it's a conference with major, focus on disasters, civil protection, water, resources and risk. So you will have other people, and you will be also challenged to present. And then we finish around 6 p.m. So without, I want to name them all. Actually, I hope I won't forget anyone. Fabio Castelli. This workshop was born here in a dinner in Florence. So let's do it, because we do think the topic is really actual. Artificial intelligence, machine learning, this intelligence part with the data is really a hot topic. But I want you to look at this course as a professional opportunity for people who are Then Enrica, some of you know, Elena, there. And this is a colleague and Gerardo Tiri, not here today, but you will probably hear later. All these components are, we have ongoing projects going on. Maybe we'll get the chance to know each other in coffee break. So there is water, we have also a European project going on. Apart this, there are colleagues and friends. And then there is the first one is the one that is the organizer of the Expo, is allowing us to be in this project. The conference. And then are Copernicus, national and Copernicus search unit deployed. Copernicus satellite, you know it, providing data services that we're also using. And then there are on the names, Polarization, Mario Concini, Chiara Righi, Laura Selvardi, Davide Alzari, and the one I know better. Sorry, Tommaso. Okay.
No.
I'm the one just speaking out. They are the one that will be your tutor. Your buddies, because they were the one that will be the introduction to the tutorial and then the training. So there are enough tutors for the groups, almost one per group. So we want you to push you to do the project in really one day. So the organization of the finishing
Che c'è?
Yes. Yes, just one finished. Just the agenda is Fabio Castelli, introduction to remote sensing, Fabio 15 minutes. And then Giulio and the others, the tutorial. That's it. So the entire agenda is very simple, no technical work. Giulio, go ahead.
Yeah, thank you very much. I hope you can hear me. Okay. So I just want to show quite new results of the projects. Because Fernando correctly mentioned the validity in Copernicus services. Okay, this is just to mention that the University of Florence has which is basically a cooperation between departments. Now, observation analysis is also with Copernicus European Earth observation system. Thank you very much. And you can see that we are doing also our activities for Google Earth Engine and Copernicus service. Just to say that these are basically all of us receiving these results changes. Okay.
I'm sorry, I have to interrupt you because we have a lot of interference from the audio. I think that there is one microphone on the participants.
Let me check. Can you mute it from there?
Yes, thank you very much. Now is very clear.
Okay, so welcome again. A question first. How many of you have some background on the technology of remote sensing? Not just knowing that there is remote sensing and seeing pictures, but how many of you have some basic concept besides the one that are following the course with me? Okay, on what really remote sensing is? More or less? Okay. So for some of you, it will be a repetition of concepts you already know. For the other ones, I will try to condense in really 10, 15 minutes a few basic concepts that you need to know to understand why remote sensing products have some characteristics. So I prepared a very short presentation on this. Okay. I guess I need to, okay, it's already showing the screen. Okay. Of course, as you know, remote sensing technology is a huge field. Today we talk about space economy. There is a whole economy around remote sensing. Okay, so to condensate in 15 minutes, this very broad is not easy. So I will try to focus on at least 3 basic concepts, and they are very important, at least from the user perspective. Otherwise, you risk of using remote sensing products without knowing why they have some characteristics, what are the sources of error, why, as a first concept, I will move rapidly through this concept, the first very important concept, why remote sensing is not just taking pictures from the space. Okay? Remote sensing is based, as you may know, based on measuring radiation. And radiation covers a huge range of wavelengths or frequency, not just the visible part, the one that we see, that we detect with our remote sensing device, that are the eyes, okay, which is a very narrow, very narrow part of the spectrum, okay. Photography uses only that part of the spectrum. Remote sensing uses many, many more and wider ranges or bands of the electromagnetic spectrum, okay? So it's not just, again, taking pictures from space using the visible part, as you, let me see if I can have a pointer that works. Let me put out a pointer, okay? These are what we may call pictures from space, okay? Very high detail, you know, use the amount of radiation that is available, reflected from the surface in the visible part. But remote sensing also uses a lot, for example, the part of the spectrum which is called infrared, to detect different features of the surface. Here we have some example of a vegetation product. I will talk a little bit more as a further example further on, that use information both in the visible and what is called in the near infrared. Or another concept you may be already familiar with is the capability, as we had to do to enter this place, of detecting the temperature of a surface, reading the radiation which is emitted in the band which is called the thermal infrared. And we can detect this way from satellite also the temperature of the length of the surface of the Earth. And this is also another important part of a piece of information that can be used for many applications. Here, for example, you see the surface temperature of the Amazon basin, of the Andes, and so forth. Okay? But not only in the part which is near the visible part, what is called the infrared, but a lot of information that is taken from the satellite also use radiation in bands that are far away from the visible ones, that are called microwaves. Microwaves have some peculiarities that I don't have time to explain now. They have the capability to bear information also on the geometrical characteristics of the surface, its roughness, or what is more important for water study, the water content, okay, of movements of the Earth. This image here on the left is an image, is actually a composite of 2 images from a radar on board the satellite on the area of L'Aquila, just before and just after the earthquake. And the comparative analysis, interferometric analysis of these 2 images allow to detect quite precisely and very with very high detailed space, for example, the movement that the earthquake induce on the target. Okay, or here, for example, another example of measurements from satellites taken in the microwave range is the same range of wavelengths that you use in the microwave ovens or in radio transmissions to detect other characteristics of the surface like the soil moisture. Okay, so first concept, remote sensing is not taking pictures. It's having the capability to measure many, many more bands in the electromagnetic spectrum, each one of them bearing information on some properties of the Earth's surface. That's why remote sensing is so powerful and informative. This is again, to stress this very important concept, it is the typical example that is being shown to understand what is called this concept of measuring different bands in electromagnetic spectrum, which is called multi-spectral remote sensing. Okay, here on the right, here you see a curve, okay, of the soccer field. From a picture, from just a color picture, especially if taken from a distance, you cannot know if it is a grass or an artificial turf. Okay, it's green, no more than that. Okay, multispectral remote sensing can recognize if this is grass or it's a non-vegetation green surface. Okay, the concept is again knowing, based on knowing what are the spectral characteristics, for example, in this case of reflectance, that is how much of the radiation coming from the sun is reflected in different parts of the electromagnetic spectrum. Okay, both an artificial or a grass surface reflects a lot in the green part. They are very similar. Okay, so just looking at the colors, that is this part of the electromagnetic spectrum, you cannot distinguish grass from artificial turf. But they reflect very differently in the near infrared. Okay, grass vegetation has a high reflectance in the near infrared, while an artificial turf won't. So to detect if that is vegetation, you need also to measure in this part of the electromagnetic spectrum, not just in the color part. Okay, and this is, for example, a product is one of the most widely used satellite products to monitor vegetation that is just based on the difference of the measurable reflectance from a satellite in this part of the spectrum, the near infrared, and this part of the spectrum, the red, that we know that a green surface will emit, will reflect very little. Okay, so the larger is the difference, the more likely is the measured surface to be an active vegetation. Okay, and then there is some normalization and so forth. Okay, so quite a simple product that you can get from a satellite, provided that you don't just take pictures, okay, but you measure in other part of the electromagnetic spectrum. And of course, given the amount of the value of the index here, you can also distinguish whether the vegetation is in good health or is start to, to turn red. So if the photosynthetic activity is, active or it's not, a lot of information on the status of vegetation. Okay, because of course we expect to have different reflectance, even not just from grass to artificial turf, but also differences in reflectance also for vegetation in different stages. Okay. Second concept. No, I have to go further, no back. Okay. We cannot get all we want from remote sensing. Okay. What we sometimes we will call images or products have some characteristics that we may be interested in, okay? But there is no free choice in the technology on what are these characteristics. The characteristics of a satellite product are always a compromise. A compromise between, for example, ground spatial resolution, okay? What are the details that you can distinguish on the measured surface that may range according to the different products from meters, okay, the Google Earth type of images, to kilometer scale, those images in the microwave that I showed you before. Okay, needs to be compromised, for example, with the SWAT width. The SWAT is how large is the area of the Earth's surface that is detected or measured at any time. Okay, so here you can do a parallel with usual photography. If you have a wider view, you will distinguish less details. Okay, if you use a zoom, you will have more details. So there is all an obvious trade-off between the width of the SWAT and the spatial detail. Okay, but also the revisit time. Okay, I will go back to this in a second. How often in time you get information about the Earth's surface. Okay, and also given the importance of having a multi-spectral measurements, how many bands you can measure at any time independently. I just mentioned, the visible part, the near infrared, but there are many others, and how narrow and precise these measurements can be. So there is a trade-off between these three. And why there is a trade-off? Because there are some constraints that don't allow to have independent choices of these three, I would say, characteristics of any product. The two main constraints are the amount of measurable radiation, okay, that can be reflected, the radiation coming from the sun, and here on the right you have the spectrum of available energy at the surface, okay? Of course, there is a lot of energy coming from the sun at different wavelengths. Here in yellow is the visible part. The near infrared I mentioned before is also energy coming from the radiation coming from the sun, which is reflected. Okay. So if you measure in this range of wavelength, you have a lot of energy available to take your measurements. Okay. But for example, if you are interested in the temperature of the surface, then you have to work not with the reflected energy, but the emitted energy, okay, by anybody, according to the famous Stefan Boltzmann law, right, of the black and gray body radiations, okay? And here the amount of energy is way less, okay? It's like taking picture in the dark, okay? Less energy available. You need to move to coarser ground resolution of the image, or largest ones, which is the same, okay? Even worse if you're working in the microwave. In the microwave, okay, here is not even picture the amount of energy which is naturally emitted in the microwave. Right? That's why, for example, remote sensing in the microwave use a concept which is called active remote sensing, where the radiation is provided by the instrument with the so-called radar technology. Okay, but there is a big constraint from the amount of energy that can be used to measure. The amount of energy bringing information from a general entropy concept. Okay, so you cannot extract information, detailed information, if you don't have available energy to use for the measurement process. Okay, and also the other constraint is the satellite position. How far you are from the surface that you're measuring. Okay, there are essentially two possible choices for the position of a satellite. What is called a geostationary satellite, they are mostly used for meteorological application. Very large distance from the Earth's surface, about 36,000 kilometers altitude. What is the advantage? Having a fixed position, the revisit time is very frequent. A few minutes, but it's very far away, very coarse resolution. To have much better ground resolution, you need to move closer to the Earth's surface, and the other option, to have not the satellite fall down by gravity, is to spin very high velocity. Okay, so it cannot be fixed with respect to Earth position. Usually, this kind of satellites follow what are called a polar orbiting path. Okay, and in this case, the revisit time increases. Okay, because to visit that part of the surface, the satellite has to pass there again, and it may take from a day to several days to pass there again. Okay, these are a few examples in this slide here. Okay, for example, of two different polar orbits. There are very polar orbiting satellites that are used a lot, and you will use a lot in your application. Okay, one of the ESA Sentinels, the Sentinel-2. Okay, and another satellite has a similar instrument on board that measures similar bands, which is the couple of satellites, Aqua and Terra, that brings on board the MODIS instrument. You will use a lot this product from these two satellites. Here you have a comparison of the bands that are measured by these two satellites. Okay, you see that both measure in the visible, in the infrared, in the near infrared. Okay, the MODIS measured also in the thermal, the Sentinel doesn't. But if you focus in this part here, you notice, first of all, that the MODIS has a much higher spectral resolution, more and narrower bands that are measured independently, a lot of information, okay? To the cost of a coarser spatial resolution, okay? A coarser spatial resolution that will be also to a larger slot, okay? So these MODIS products are characterized by higher spectral resolution, lower revisit time because of a larger swath, daily revisit, much coarser spatial resolution with respect to the Sentinel-2, that to the cost of a lower spectral resolution, narrower swaths, so revisit time that according to the position may increase up to 10 days to have a new measurement in the same place, but a much higher resolution. So it's an indication of a trade-off between these aspects. And of course, if the user that according to its application prefer one product if you need to have a more continuous revisit, but is enough to have this type of resolution. Oh, I don't see any microphone on. Let me, okay, maybe now it's more stable. Okay? Okay, so let me finish with the first concept, okay? Satellite, and here is what we may connect more to the word intelligent that was in the title of the workshop, okay? What are called products, Earth observation products, are not just the satellite measurements. There is a lot of intelligent post-processing in it. Satellite measures radiation, okay? Products, you may have products that range from, you know, the some index on, here is an index of area or detecting the area that has been burned by a fire, okay? Up to very advanced products in terms of, here is an example of net evapotranspiration. Of course, these are things that are very distant from the simple concept of measuring radiation, okay? So there is a lot of post-processing on top of the measurement taken from the satellite that needs a lot of model, ancillary information, intelligent data use to achieve what we see as used as products. That is good to, it's important to know that there are different levels of products. And again, according to the application, you may want to use what are called the level 1 products that are just the measurement georeferenced and corrected for clouds and so forth, but just in terms of actual radiation. Here, for example, is a product, level 1 product from Landsat with the false colors where the 3 bands are composed not using the red, green, and blue measurements, but the measurements in other bands. Okay. Here is a level 2 where these are interpreted with even very simple formula to get what are called a geophysical variable. In this case, burnt areas. Okay. Or level 3 and 4 products where more information is added, other data from the ground or from other satellites, complex model, okay, to get products that are, again, very, very advanced, like the estimate of the surface flux. Okay, so I finish here. I hope I give you some pills, okay, very basic concept. Without this, it will be not easy to understand how to navigate in the huge amount of products that are out there that can be accessed in the way that you learned this morning. Okay, so thank you for your attention.
Thank you, Fabio. Yes. So very informal, without any further introduction. Thank you, Fabio Castelli. So one of the students will start, and then the others will follow with Savelli from some theoretical, and we'll go into the technical part. Okay. And you will see what the introduction that Fabio Castelli gave you is how to put into practice using the satellite data within the Earth-20 platform. That's Savelli will introduce you now. Okay, Savelli, go ahead.
Okay, so good morning, everyone. I am Saverio Francini, PhD student from the University of Florence. So today is a workshop on Google Earth Engine. So let's start to see what Google Earth Engine is. So Google Earth Engine is a cloud platform offering planetary scale analysis capabilities. So one of the main challenges of remote sensing is to manage big data. So we have a lot of images acquired everywhere in the world. And this is usually something that is very complicated to be done using a normal workstation. Google Earth Engine offers a lot of computation capabilities for free, and this is the main advantage. And in addition, it offers a multi-petabyte catalog of satellite imagery. So on Google Earth Engine, there are ready to be used a lot of different satellite images acquired from a lot of different satellite missions. As I was saying, Google Earth Engine offers a huge amount of data, pre-processing of images already done. So as the professor was saying before, pre-processing of satellite images is something that has to be done and is something that, again, requires computation capabilities and that can be challenging. An additional advantage of Google Earth Engine is that this pre-processing is already done. And again, Google Earth Engine is fast, so you do not have to wait a lot of time to obtain data, but images and products are obtained in a few seconds. And again, it's free. So Google Earth Engine is used for a lot of different tasks. So it's used to monitor forests, to monitor water, to monitor dynamics, changes over time. So for this reason, actually, although it was published in 2017, this paper, the paper of Google Earth Engine, has been already cited 2,000 times. So a lot of times just in 3 years. And yeah, so as I was saying, I'm a PhD student in Florence. I spent some time in the University of British Columbia, and I worked in Canada, and I worked with Mike Fulder on the implementation of the best available pixel procedure. So this is one of the applications of Google Earth Engine that are available online. Meanwhile, I worked with Noel Gorelick that is the creator of Google Earth Engine, as you can see from this paper, and we are working together on the implementation of a forest change detection and monitoring algorithm. Sorry, I don't know if we have a question, but I wasn't able to have. Okay, so this is an example of an application that can be implemented on Google Earth Engine. So this is an application that shows the Sentinel-2 images acquired in the last 48 hours everywhere in the world. So as you can see, it is interactive and it is very fast, and you are not expert with remote sensing data, but you have to know that this kind of data requires a huge amount of memory. So here we are looking at terabytes of images, but in this way, these images are in the cloud, are in the Google servers, so we do not have to care about this, and we can just load the portion of data that we want to visualize or analyze. Doing this on a workstation is impossible. This is a different application we developed. This is an application that allows to construct different cloud-free composites and to visualize different cloud-free composites. So we will talk about this soon. One additional challenge of satellite images is that there are clouds. So ideally, you do not want clouds on your image because you need information of the surface. So there are a lot of procedures that allow us to mask out clouds, so to remove clouds from the images. And then there are additional procedures that are called composites or cloud-free composites calculation that allows to obtain valid observation also for those pixels that are covered by clouds. So here, for example, we are looking at a forest fire that occurred in Sardinia this summer, and as you can see here, we cannot see a lot because we are not using the right bands, but now we changed bands, and as the professor was saying before, using the near infrared, we can see very well the forest fire that occurred in Sardinia this summer. Yeah, this is another application that we implemented that allows to detect forest change and to produce area estimates. So we obtain these maps. Blue, what is blue are forest change occurred in this case in 2018. And this application allows also to produce area estimates and confidence intervals. So I think that's it. And we can start to try to use Google Earth Engine together. So I hope you all have a Google Earth Engine account. You should have a Google Earth Engine account. So please open the code editor. And please let me know when you are ready.
Make sure everyone has access, also asking like.
Yeah.
And everyone has the account.
And you online do have a Google Earth Engine account. So I hope we sent you an email to tell you that Google Earth Engine account was required for today, in particular because if you create a Google Earth Engine account, maybe you have to wait some time before you're able to use Google Earth Engine. So I hope that you already have an account. Otherwise, just create it now, and finger crossed that you'll be able to use it soon. So if you're ready, I can start to share you. I can start to share you how the code editor, how the Google Earth Engine code editor is organized. So an additional advantage of Google Earth Engine is this code editor that is very simple to use, and that includes a lot of features. So we have three main windows: left, central, and right. Okay. Okay, I'm waiting a couple of minutes. So, online people, are you able to hear me? Are you still here?
Yes, thank you.
Okay, great. So please, if you have any question or if you need to ask me to wait, just tell me, please.
Thank you very much.
Thanks.
You're welcome. We are just waiting that everyone has opened the Google Engine for that. After that, we can start to see how it works. So have you some experiences with programming, some of you? No, zero. And you online, do you have some experiences with programming in general, maybe R or Python?
Not a lot, but some simple codes.
Okay. Okay.
For me, I don't have experience.
Okay. Okay. So the programming language that we are going to use today is JavaScript. It is a little bit complicated, but how it is used in Google Earth Engine is very simple because a lot of complicated operations have been already done. So we just have to select images quickly. We are going to scriveremo a mano. Questa è l'idea. Allora, ora li guardiamo insieme e voi cercate di scrivere. Poi dopo vi diamo un link che vi permette di accedere a tutti i codici che abbiamo visto. Però non vi vediamo, se no è troppo facile. Sì, cliccate là. Okay, so are you ready? See? Okay, so this is the Google Earth Engine code editor. We have three main windows, left, mid, and right. Here we have three sub-windows. We have the scripts, the documentation, and the assets. So the scripts is the window that is used to store your codes. Here you can create new repository, new folder, and new files, where files are, for example, this one, so are the scripts, so are the files that are used to store your code. Here you have some subsections. So you have the writer section that includes the codes that you wrote, and you have the reader section. So in this section, you'll see appearing the codes that you are using now. So we are going to send you a link that will allow you to visualize our codes later.
And interrupt you a second, just a second. Non ti seguono male. Di mouse. Vecchio, per farlo più grande.
Quello forse era prima, era prima?
No.
Ah. La velocità del puntatore era
Per farlo più grande, allora, che cazzo. Pensavo di metterci un secondo.
Forse cambiare la combinazione.
No, volevo fare il puntatore più grande, ma questo è un Windows vecchio.
opzione puntatore? La velocità no. No, la velocità no.
Però si può, ad esempio, selezione quando clicchi si fa
Posso cercare di muovere il mouse più lentamente.
Ma già così
Sì, si vede, sì. Okay, so we are back. And yes, I was saying that we are sending you soon a link that will allow you to visualize the codes that we are going to see together now. So the documentation subsection, subwindow is very useful. So is the window of the documentation. So here you can find 4 functions that are built in Google Earth Engine, so that are already ready to be used. For example, the filtering functions, and for example, clicking on this function, you can see how to use this function, the description, what is the aim of this function, and what are the arguments of this function. We can see this better later. After that, we have the assets sub-window. So this window is used to store your own data. So in Google Earth Engine, you can use a lot of data that is already in the Google servers, but you can also upload your own data. So for example, you may want to upload a shapefile. Do you know what a shapefile is? Yeah, you can, for example, upload a shapefile of your study area, and then you can process this data. But you can upload also images or CSV files that are tables like Excel files. Here we have the window that is used to write links. We'll see this window better very soon. And then here you have a lot of very useful options. You have the get link options. So when you click here, a link is created, and if you share this link with someone, that is this link, and the user, your colleague, will be able to visualize and use your code. So it is a very quick and useful way to share codes and data. Actually, this is the button to save your file, your code. This is the button that is used to execute your code. One important point in Google Earth Engine is that you cannot decide which line you want to execute, but you have all times to execute the whole code at a time. Okay, so you have to click run or to press Control and Enter together, and the whole code is executed. You cannot decide to execute just, for example, lines 8 and 9. The reset button is used to clean the console. That is what we have on the right, and the map. So what we are, if you are visualizing a map, clicking on the reset button, the map will disappear. This button is used to create applications. I hope that we will have time later to see how to use this option. On the right, we have the console window. That is where outputs are printed out. We can see this again better later. And we have the inspector. The inspector is very useful because it allows you to visualize values of the map. So if you click on the inspector, and if you click somewhere in the world, because we are not displaying any map now, you are able to see just the longitude, the latitude, the zoom level, and the scale. So a very important point in Google Earth Engine is the scale. So Google Earth Engine is very fast for a main reason, for a lot of reasons, but the data is already there, is already in the Google servers. So what you are doing is just sending the code and asking for some kind of this data. But the important point is that the computation is performed at the scale at which you are visualizing the map. So if you are visualizing the map at this scale, a pixel has a size of 1 kilometer, and computations are performed using pixels with this size. So here we have, for example, 3,000 pixels at this scale. But if pixels would have a size of, for example, 10 meters, you would have billions of pixels, and the computation required would be much greater. So we can talk about this again later. The console, we can see this now, and then the task is the window that is used to export data. So when your code allows to export images or tables or shapefiles, then you'll see here appearing some buttons that allows you to export data directly on your Google Drive account. Okay, so we can start to write code. So create a new file. To create a new file, you have to go in the scripts window, have to create in the new button, and you have to create a new file. Here, I already created a new file. The name is Hello World. Online people, are you still there? Were you able to follow me?
Yes.
For me, thank you.
Okay. Let's do some exercise. Let's see your Okay, so we have created this new file, and we can, of course, write a lot of things. The first thing that I want to show you are comments. So when you are writing a code, it's always important to write a comment. So this is my first code, for example. When you have a complicated code, it is important to write what each line of the code is doing, because if you are going to open the same code after months, you would not be able otherwise to understand what you did. This is a programming language. It is called JavaScript, and in these programming languages, of course, you can create a lot of different objects. To create a new object, you have to type var, meaning that I'm creating a new variable. Okay, so var, and the name of this var, for example, can be people. So I want that people is a number. So, for example, 7. And semicolon. So in Google Earth Engine, at the end of each line, you have to use the semicolon, okay, in JavaScript. more in general, not just in Google Earth Engine. So here we have created a new variable. Of course, you can define a different name and you can define a different number. We want to see if we were able to create a new variable, so we can use the print function. The print function allows you to visualize the output in the console. So here you can see that the console is orange, meaning that something happened. And if we go here, we can see that the number is printed out. We can give also a name to what we are printing. So the print functions takes 2 arguments, and this is useful to start to understand what arguments are. So the arguments are the objects that the Google Earth Engine function requires to execute a code. So the print function takes 2 arguments. The first argument is used to define the name of the variable that we want to print, and the second argument is the variable that we want to print. How's it going? Were you all able to print an object in the console? What's going on? So if it doesn't work, it's because you made a mistake in typing some of the characters. And this is very common in programming languages. So you have to type var to create a new variable. After that, there is a space. And then you can type whatever you like to create the name of a variable. Then you have another space. Oh, no, okay, this space is not mandatory. Then you have the equal symbol, that one. And then you have. Okay, so one moment. There. Click run. And now you have the object in the console. Okay. So sorry, guys. So sorry, guys. Of course, after you created the code, as we said before, to visualize the output, you have to click run. Here we got an error because people does not exist. The error is people is not defined because I changed the name of my variable. Now the name of this variable is something strange. So if you do not click the run button, anything happens. You have to click the run button. So variables can be in Google Earth Engine numbers, but can be also characters. So for example, I want to create a character variable. The name of this variable is char. And the value is, for example, the capital letter A. Again, we can try to print this object. So this is a very boring part, but to start to understand how the code editor works, I think that a few minutes of this can be very useful. So here, for example, we created a character variable. In the next script, we are going to start doing more interesting things. And we can create lists. Lists are very useful in Google Earth Engine because it allows you to store different objects together in the same variable. So for example, a list of numbers, and we can print also the list. Without that was better. So a useful thing to know is that, as you can see, this is a list. So here we have a list that includes all numbers we wrote inside this list. An important thing to know in Google Earth Engine is that you do not have to write everything, but you can press Ctrl and space together to receive some suggestions. So for example, you can type just P, and then you can press Ctrl and space together, and then the print function is suggested. Then you can press Ctrl and space again, and the arguments are also suggested. For the print function, these do not appear to be very useful, but for example, for a function like this one, you can see that now you have already all the arguments that the function required here without having to go into the documentation. So we are going very fast, but we have just one day to do a lot of things, so we have to do like this. Another object that we can create on Google Earth Engine, probably the most important object, is images. So we can create a new object. The name of this object can be, for example, Pluto, and this object is an image. To create an image, we have to use another Google Earth Engine function that is ee.image. This image takes a lot of different arguments. One of the arguments that can take is a number. So what we are creating now is an image that is 8 everywhere in the world. So it's something meaningless now, but try to understand that creating an image that is 8 everywhere in the world on a normal workstation is something that would be very challenging, because are anyway a lot of 8s, because we have billions of pixels everywhere in the world. So a lot of data is needed. We can print this object. And you can see that this time you have an image, and that this image has one band. We can have more information. Okay, can use the mouse maybe here. So we already know that this image is a constant, because as we said, it is 8 everywhere. And we have also the reference system and the data type. The data type is integer, because 8 is an integer number. And we do not need floats. That is the data type that is used to store decimal numbers. Because we have an image, we can also visualize this image on the map. We cannot, of course, visualize numbers of this map, but we can visualize images. To visualize an image, we can use the map.addLayer function. Add layer function, and we can type inside this function Pluto. That is our image. We can again click run, and at this stage you can see that it's black everywhere. It is black everywhere because everywhere we have the number 8. To double check this, we can use to double check if the pixel values are 8. Exactly, the inspector. So we can use the inspector, click somewhere, and we can see that the value of that pixel is 8. So we have this image, this black image that is again meaningless, but it is everywhere in the world. Again, this is very fast, because at this scale, these pixels, the pixels that we are looking for, has a size of 78 kilometers, 78 kilometers. Okay. Otherwise, we would have a lot of pixels, and the computational time required would be much greater. So this was the Hello World code. We are going to send you a link. You can find this. One last thing that I want to show you is the multi-line comment. So if you have to write multi-line comment because you have to because you have a very complicated code and you have to write a lot of things, you can use this this option. So doing like this here, you can write whatever you like. Okay. And one additional advantage of this is that allows to write comments inside the code within the same line of a working of a line where the code is working. Okay, here we have we start to see more complicated things. I don't know if you have already access to the link of the codes or not. Giulio gliela inviato i codici, i link ancora. Okay, so but we can do it at the end of this of my presentation. So you have already the link for having these codes on your Google Earth Engine account, but it is better if now you just look at my screen and you just understand how this code works. Later, we are going to send you this code and you'll be able to use this code. But now you do not have time to write all codes line by line because I want to show you a lot of things and we have to do it in something like 10 minutes. So this is a script that can be used to detect changes, land cover changes, forest changes, water changes, whatever you like. So this script, this code allows to construct two different cloud composites and then to detect differences that occurred between these different images constructed over different periods. And these differences are detected using actually complicated functions that is called Euclidean Distance. So because we have two pixels, we have two different observations of the same pixels, we are able to detect changes between these pixels. So changes are differences that occur in the band's values. One of the things that can be done to detect changes is to calculate the Euclidean distance. So for each pair of bands, we calculate the difference and the square difference. So this is a measure of spectral distance between two pixels. Anyway, we don't care a lot about this function. What we care is that we are going to detect differences between two pixels values. The first thing that we do in this code is to load an image collection. So doing it in Google Earth Engine is very simple because we use the image collection function. And in this way, at line 2, what the S2 object is an image collection that includes all Sentinel-2 images acquired everywhere in the world. So terabytes and terabytes of data. And what we want, and what we are doing here is just to filtering images based on a cloudy pixel percentage. Okay. So we do not want to select images that are completely covered by clouds. We want to select images that are covered by clouds less than 20%. So this is a random number. Here you can type whatever you like. So you can see this later. This may be an argument of your function or an option for a user if you want to construct an application. This is another data set. So as we said before, we want to mask out clouds from images. Okay, to do it, Google Earth Engine offers a very useful data set that is the Sentinel-2 cloud probability dataset. So this dataset says for each Sentinel-2 pixel of each Sentinel-2 image, what is the probability that that pixel is covered by clouds. Okay, so using this data, it is very simple to mask out clouds and to remove pixels that are covered by clouds in our image. So first we select images that are covered by clouds, in this case, let's say less than 20%. And then we are creating a new object that is the image collection that we want to use to mask out clouds. Okay. Here we are doing a complicated stuff, but what we are doing is just to associate for each Sentinel-2 image the right Sentinel-2 cloud mask. And to do it, we are using the join function. And as I was saying, we want to join as primary image collection the Sentinel-2 image collection, and as secondary the image collection that includes the clouds mask. And then we want to say that the condition to merge these image collections has to be the system index. So we want to merge images that have the same system index. Okay, and this is an important stuff. So we have an image collection that is this one, that is Sentinel-2 with cloud mask. We have an image collection that for each image includes a cloud mask. So what we want to do is for each image in our image collection to use the cloud mask and mask out clouds. To do so, we can create a function that is another type of objects that can be created on Google Earth Engine. So we create a new variable. The name of this variable is mask clouds, and this variable is a function. Is a function that takes one argument. In our case, the argument of this function is an image. So for each image, we want to get the cloud mask because we have added that cloud mask to that image. And because that image, that cloud mask for each pixel says the probability that that pixel is cloudy, we want to apply a threshold. A random threshold may be 40. So like this, we are saying that the clouds mask has to be less than 40. That's why here we type LT, because we want that pixels have to be a probability, should have a probability to be cloudy smaller than 40%. Okay, and because this is a function, we have as a last step to use the return argument. The return argument is used to specify what the output of our function should be. And the output of our function should be the input image, but masked using the mask function with the is not cloud mask we create. Okay, and this is a very important thing. So we have to apply the same function on all images in our images collection. So we have thousands and thousands of images, and in this way we have just to create a function, and then we can use the map function to apply this function on all images in our image collection. So at this stage, we are mapping the mask cloud function. So don't look at this for now. So we do not have clouds anymore in our images. We want to construct two different. Okay, here we are printing an example. So because, as you can see, okay. For example, here at line 30, we can print the object we just created, and you can see that we have an image, and that this image is a Copernicus Sentinel-2 image, and that this image has 16 bands. So these are the Sentinel-2 bands. So bands 2, 3, and 4, for example, are blue, green, and red bands. Okay, we are in an important moment now because we have an image collection without clouds of Sentinel-2 images acquired everywhere in the world, but we want to detect changes. So to detect changes, we have to construct two different images. Okay. To do it is very simple. So we can use the filter date function. So at line 28, we want to create a cloud-free composite of images acquired between between August 5th and August 31. So using the filter date function, we are selecting just images that are acquired in this period, and then using the median function, we are calculating for each pixel the median of images or pixels values of images acquired in that period. So we have a lot of pixels observation for that period because a lot of images were acquired in this period, but we want just one pixel value, so we calculate the median. Of course, the median is calculated excluding pixels values that are covered by clouds because we masked out clouds. We then do exactly the same thing, but for 2021. So we select images that are acquired between 2021, 8 August, 5 August, and the 31 of August. And so now we have two cloud-free composites. One cloud-free composites of images acquired in 2020 and a cloud-free composite of images acquired in 2021. So we have two images, and we can look at this function better later. So if some of you wants to construct a project that is using this code, we can look at this function better later. But for now, just know that we want to detect changes between two images. And so we are creating a new function. The name of this function is Euclidean Distance. And this function takes two arguments, image 1 and image 2. So the image from which we want to detect changes. And indeed, in line 40, we are using this function. So we are creating a new object. The name of this object is ED, that is for Euclidean distance. And this object is equal to the output of the Euclidean distance when used with the two cloud-free composites we created. So, and we have finally finished that code. So at line 42, we want to see what we did. So at line 42, we are visualizing the output. Okay, because we are using at line 42 and 43 the map.addLayer function. So as I was saying in my first presentation, this summer in Sardinia, a very huge forest fires occurred. And it was in the first days of August. For this reason, I selected these periods. So we are comparing images that were acquired in the same period of the previous years, but when the forest fires was not occurred, and then we are with images acquired after the occurrence of that forest fire. And as you can see here, we can see very well that a lot of pixels are green, so have small values because anything changed during that period. While here we can see very well pixels with large values of Euclidean distance, meaning that in these pixels between these two periods, something wrong occurred. So a huge change occurred. In this case, a forest fire. We are looking at green, red, and yellow because, as you can see in the map.addLayer function, I defined these colors as the palette. And I also defined that the minimum and the maximum values. What these values mean? These values mean that pixels where values are 0 should be green, pixels which values are 2000 should be yellow, and pixels with value are 4000 should be red. Okay. So because we have this image, we can apply a threshold on this image. And is what we are doing here using the GT function. Before, the LT function was the function that was used to apply a threshold less than. This time GT is for greater than. So we want to visualize just pixels that have values greater than 2000. And indeed, if we open the layer here, we can see that you can see in red pixels with values of the Euclidean distance greater than 2000. So in 50 lines of code, we have detected changes, and we have actually implemented a forest change detection algorithm that can work over different periods everywhere in the world and at different scales. So doing something similar with a normal programming language is something that requires months. As a last step, I wanted to show you, okay, here we are looking at the map.centeredObject function. So this function is used to center the map on a specific region. And I use this function because I wanted to show you that region in Sardinia, that forest fire. And the last function is the export.image2drive function. So this function is used to export the image. So if you want to export this image, these changes that you detected over a specific region, you can use the export.image function to drive. And at this stage, as I told you, in the tasks window, you'll have a new object. If you click run, you can define the drive folder name, the file name, and after that, you'll have a raster image on your Google Drive account. Okay. of the changes you detected. So we can see one last part very quickly. Yes, so this is another code. As you can see, the name of the code is the same as before, but with fun at the end. That is for function. So what we do here? So just trust me, but these brackets includes exactly the same code that we have seen together now, okay? If you remember well, in these codes, we use some parameters that, as I said, may be options for a potential user of your application. One parameter was the cloud threshold. I used 20, but users may want to use a different threshold if wants to apply the algorithm in different areas. For example, in Canada, where there are a lot of clouds. So if you use 20 as cloud threshold, you have no images, and then you have to use 70, for example. And then our application, our code allows to detect changes between the periods we specified, but a user may be interested in detect changes between two different periods. So what we do here is to specify to our function some arguments. So this function now, the code we saw before, now takes 5 arguments. So it takes the cloud threshold, the start date of the first image, the end date of the first image, the start date of the second image, and the end date of the second image. So in this way, a user is able to specify different time periods, to construct different cloud-free composites, and then to detect forest changes over different periods. As a last step, because we have created this function, we can create a user interface. So again, if some of you in these projects want to create something similar, we can see this code better later, but how it works. So it works like this. So this code allows to create a panel on the right that allows to define the input parameters we are talking about. So as I said, our function now takes 5 arguments, the cloud threshold, and is this one, then the start date, then the end date, and of the first image, and the same thing of the second image. Then we have a couple of buttons. We have the run button and the reset button that is used to remove layers. So in this way, we have created an application that can be shared with other users and colleagues everywhere in the world. The useful thing of this one is that it can be used without requiring coding expertise. So a user can just type some parameters and click the run button. An additional very useful thing is that at this stage, you can use the app option to create a new application. Okay, you can use the new application button, and here you can provide a description of your application. You can upload an image that is the background of your application and so on. And the advantage of creating an application is that it can be used also by people that does not have a Google Earth Engine account. So this is a very useful thing because you just have to have a Google Earth Engine account and then you can use this code button. If you want, for example, to put this application on a website, it may be better to create a real application using the button I was showing you. So I think it's all for me for now. I don't know, Giulio now or no so. Okay, so online people, are you still here? Everything fine?
Yes, we are here. Thank you.
Okay, do you have
Thanks.
Do you have any question?
Can I ask a question?
Of course.
What happens if the calculation of the Euclidean distance to find the pixel that was masked out before previously?
Yeah.
So you have the image which has some holes.
Volevo usare la lavagna, ma poi non c'è. Comunque, for each pixel, in the period we selected, we have a lot of observations, okay? So in that period, because the visitation time of Sentinel-2 is 5 days, in that period we have, for example, 4 or 5 values, okay? Let's say that in a couple of images that pixel was masked, was covered by clouds. So now we have 3 values, and now we are calculating the median of these 3 values. So now we have just 1 value for that pixel. So in this case, this is why we calculated cloud-free composite, because we wanted valid observations also for pixels covered by clouds. But actually your question was right, because it is possible that in some pixels, was covered by clouds in all images acquired over that period. This can happen. And at this stage, when you calculate the Euclidean distance, you get a masked pixels because you had not valid observation for that pixel. But yes, it happens.
Is it convenient or possible, convenient to transfer these functionalities to images of the activities?
So there is. So what Google Earth Engine staff suggests is to use this code editor because it's very useful and because it includes a lot of features that we had no time to see now, but it is a very good code editor. Anyway, there is a plugin for QGIS, but I think that is not working. So so far it has a lot of bugs, but they are working on it. And there is a package that is RGE that allows to use Google Earth Engine from R, but actually, even if you are using R, the programming language is still JavaScript or something very similar. So if you learn how to do it in JavaScript, then you will be able to do it also in R or in Python.
But what happened to the masked? Just put a value.
Exactly. When you mask a pixel, actually, you are writing in that pixels no data, or or whatever you write. Yeah.
This example, we use the Sentinel to go. If you want to move to another platforms, there is a list or some features that we can use because I think that we have a database collected in Google Earth with all the satellite products, but we need to know which kind of product.
Yeah. The best thing is to go on Google, and if I remember well, Google Earth Engine datasets. Exactly. And here you have the catalog that is very well done. You have the catalog, and it includes exactly a search window here. So for example, if you want data sets that refer to water, you can write water and you have a lot of suggestions. And then here you can find anyway Landsat, Modis, Sentinel-1.
Yeah.
You're welcome. Okay, so I give the floor to Giulio.
Okay, thank you very much. I hope you can hear me home.
Yes, thank you.
Okay, so just going to give a short presentation, but the presentation you will see that is basically the part of code that I will show. So I will use this visualization here, so it's easy to shift from the presentation to the code editor, okay? And just one quick thing from Saverio. If I load another script, the application will go away. Okay. So, thank you very much. My name is Giulio Castelli. I'm a researcher at the Department of Agriculture, Food, Environment and Forestry of the University of Florence. And together with Professor Elena Bresci, Camilla Di Bari, and Laura Stendardi, we are presenting this case study that is slightly different from the case study that Saverio presented, and it shows you how you can use Google Earth Engine also to generate data in the form of time series. So basically, the idea is that Google Earth Engine is not only nice for having images or change detection on a spatial area, but is also very, very, very useful if you have to get one data across maybe a long time series in one point. And this is very, very useful because I don't know how many of you have experience of use of remote sensing before cloud computing. But what you had to do was basically to download a lot of megabytes or gigabytes of satellite images on your laptop to get the value in one point. Okay, and with these tools, this is radically changed and is quite more easy. Okay, so let's go a little bit on the background of this exercise. So actually, we are working in a mountainous area, and this exercise is developed from a live project. The name is Pastoral. I'm not working in it, but I'm working with data similar to the ones that they use here. And the idea is to enhance the capability of monitoring the productivity and the role of pastoral agroecosystems in mountain area. In this case studies from the Italian Alps. So the objectives are actually to show you how you can select time series and how also you can calculate vegetation indices and how you can actually extract the time series of the indices from the Google Earth Engine. We will work in the Gran Paradiso National Park, and you will find that we will show 3 types of pastures, which are at different altitudes, and through the Google Earth Engine, we will see how these pastures are more or less productive in different times of the year. And of course, you have the link to the database. This Fabio Castelli already shown. So this is the index that we will use, the normalized difference vegetation index, that is basically normalized difference between the near infrared and the red wavelength. And it gives you a feedback on the health status of the vegetation. So if the value of the NDVI is close to 1, it means that the vegetation is doing a lot of photosynthetic activity. While if it's close to 0, it means that the vegetation is not doing photosynthesis, so it's not growing. So a vegetation that is productive, a pastoral system that is going to restore a lot of fodder for animals, has a very high NDVI, or let's say an NDVI close to 1, because 1 is the maximum limit for these index. Okay, so let's now jump to the Google Earth Engine. I think you should have the link for this exercise, that is the GEE PNGP. So this is just to check that everyone is here, okay? Is it fine? You are at this point? So the link should be in the, you should have access to the drive folder. Tony, have you sent them the link to the drive folder?
Yes. The shared folder which you can find for us is the link, the Google Doc.
Ok, did you share materiale didattico?
No, it's in another folder. The ones I sent you yesterday to the students, which there are only the PDF.
Okay, so the only important thing is that you can copy and paste the code in the code editor. Because I will go with copy and paste. Okay, so you will have actually, let's do it together. You will have, let's make a new script. No, loro hanno il link solo ai PDF. Hanno il link solo ai PDF, non hanno il link no.
Prof, I think we have also the link. I have the code now in the folder tutorials and presentations that has been shared.
Okay. Okay, so you have also the link to the codes. Can you access them?
Yes.
Okay.
I accepted.
Perfect. So we don't need this. So you are with this code, correct?
I'm sorry, when I can't find the link.
Okay, so let me try to go from scratch.
I just shared it in the chat of WebEx.
Okay, thanks.
Okay. So you should have all the link to this folder, okay? Where you have all the presentations and you have also one file with link to the repository. So if you click here, you will have on your Google Earth Engine panel also this folder. So I repeat again, so in the share folder, you have this file that's called link to the repository. If you click the link, you will be redirected to the Google Earth Engine, and you will find in your writer tab one folder with all the exercise that we will show today. Can you find it? Is that going smoothly home?
Yes, for me it's okay, but I don't know for the others.
Okay, it seems that we are getting there. So everyone.
For me, I find. Excuse me. For me, I find the link. Thanks.
Okay. So actually, you will have the code only as reader, okay? So if you want to edit this code, what I suggest is that you copy all the code, okay? You copy all the code, you create a new file under your personal folder, and you call it my tutorial 2. And in the new folder, you copy all the code from the exercise. And then you save it. Okay, so in this way, you can have this code in your availability, you can copy it, you can reuse part of it, and so on and so forth. But the first thing that you would have to do, otherwise the code is not working, is to select one study area. And I don't know if Saverio show you, but basically what you can do in Google Earth Engine is to use some drawing tools. Okay, so for instance, you can draw new geometries on the map. So if, for instance, you want to draw a rectangle, you just need to click this icon, and then you draw a rectangle. So when the rectangle is drawing, you will see that already Google Earth Engine imported in your script the new rectangle as a geometry. And then you save the new script with the geometry, because we need a geometry to run the script. So I will be now very quick, and I will show you step by step how this script is working, and then we will run. Because very easy, just to show you how the script works. So you can follow basically directly on the code while you are looking at the slides. So the first thing to do is to select a study area, and this is what we did by the rectangle. Everyone should have a study area. Then you will see these instructions, and you will see that the pastor with the higher productivity are the lower ones. And basically, this is the instruction to insert a new point. Var point h, this is the name of the variable, ee.geometry.point, and then within brackets, you have the coordinates. Okay? So we are selecting now 3 points. Of course, this is a slide, but if you check the code editor, you will see that Google in automatic is giving you different colors for different parts of the code. So for instance, if you have a double slash, the code will turn green because it's a comment. While the instruction automatically, they turn purple. And the figures, so numbers, they are blue or light blue. It's very useful because it's quite interactive. And if you click or if you move the mouse around, it will tell you if there is something, if you can add something or whatever. And you have also quite a good system of alerts. For instance, if I remove this, I will get an information. Missing semicolon. This means that the semicolon is missing. So with these advices, the Earth Engine is telling you the code is not perfect. While if you make some errors, you will give you an error message. You see, here he is telling you, hey, I'm expecting you that this line is not closed by semicolon and that's all, but I'm expecting you closing the brackets. And if you close the brackets, the errors goes away. So this is quite a good tool for debugging. That means to find the errors in your code. Then, to which point we add a buffer. Do you know what is a buffer? A buffer is basically one area with a radius around your geometry. So in this case, we are creating other variables, other objects in the code, which are not points, but are buffers. So basically, we are creating a buffer at a distance of 20 meters. So we are creating some circles with a radius of 30 meters around our points. Okay, and again, you see here that, for instance, point H dot buffer open brackets distance, you see the different colors. So point H is black because we are referring to the variable point H. Dot buffer is purple because it's the instruction. Then distance is red because it's an attribute, and 20 is the distance, the number. So I'm not going into the details of the coding of JavaScript, just because this is not what the Google Earth Engine wants. So if you see the tutorial, you will find that you do not need to learn the JavaScript language to make this exercise. But you just need to get how it works and to copy and paste instructions. So this is basically the straightforward approach if you are just a final user of the Google Earth Engine. Then if you get more in touch with the code, if you get more experience, you may consider start programming properly, or maybe start using also Python for programming. But this is not the goal of this workshop. The goal of this workshop is to show you some quick activity that you can do with the Earth Engine. So another instruction that is in this exercise is the creation of a list. So basically here we are creating a unique variable which is composed by the three buffers. So we are putting all the three buffers together. And then the instructions that follows are the display of relevant geometries of the map. So you see this instruction, map.add layer. We are adding the point buffer H in the red color, and the results will be called the point buffer. The next instruction is quite important. So it's basically the generation of an image collection by Google Earth Engine data. So here we are basically generating an image collection starting from the Copernicus Sentinel database, and we are applying some filters. The first filter is quite easy to understand, is date. So we will analyze the year 2019. Then we are going to apply another filter that is on the attribute cloudy pixel percentage 20. It means that we are selecting all the images that have a cloudy cover below the 20%. And then we do not want all the Sentinel images of the world. We just need the Sentinel images which are in our study area. So we are filtering also the images with the geometry. So we are saying just take the images that are within our geometry. And then there is this instruction print S2TS. This is not meaning that we are printing on the map, but we are printing on the console. Because when you print one variable, the system gives you the variables in the console. At this point, I'm just going to run the first time the tutorial, just to show how it is scanning out. So this is the results of the first print, okay? The first print that we did gives you back what is within the S2_TS variable, which is the Copernicus Sentinel-2 database with some filters, which gives you back around 4,063 elements. I'm not showing what's more, but you can see it. But please, let's keep concentrating on the exercise. Then what we are doing, we create a function, okay? So we create one function that allows us to calculate the NDVI. So what we do is we create one variable, and the variable is a function. So I think you can understand me, because you are basically saying, as engineers slash agricultural scientists, so you know what is a function. So here we are creating one object that is not one physical object, but is just a new instruction. And this instruction, if it's applied to another object, makes a calculation. So to make the thing clear, we are creating one new application, a new function. Sorry, please close your microphone home. That if this new function that is called add NDVI is applied to a Sentinel-2 image, it makes a calculation of the normalized difference between the band 8 of the Sentinel sensor and the band 4 of the Sentinel sensor. It means it calculates the NDVI, because the band 8 is the near infrared of the band 4. So then what we are going to do is that we add this band to the image collection. So we take our old S2_TS image collection, and we ask the system to make another image collection that has another information, not only the information that we have stored in the system, but another information, another band that is the NDVI. And then what we do is that we extract the NDVI for each image. So I'm sorry, I'm going fast, but this is just to show you the code. You don't need to know the details, you just need to know that this code is doing this. Okay? So for each image, image, we calculate the maximum, and then we get the maximum, okay, for each buffer. So here what we are doing, we have all our image collection, 460 images. For each image, we calculate the NDVI. Then we have 473 images with the NDVI. We extracted the NDVI, so we have only 463 images that are only NDVI. And for each buffer, we select the maximum value across these 463 images. Okay, this can be seen again. I mean, this is a little bit niche, but it can be seen again here. So we have a feature collection, we have 3 objects, and we have 3 elements. So the first object is the first buffer, and this is the maximum NDVI. So the first buffer is the high NDVI area. And you see that here the highest NDVI value of the year 2019 is 0.9, almost 1. Then the second polygon, if we analyze the same thing, you see that is a little bit lower. So the maximum NDVI in 2019 for the second point, meaning the second buffer, is 0.64. And then we have the third one, so the third buffer, that is the lower NDVI point, and we see that here that the maximum NDVI for that point is 0.57. Okay, so this amount of instructions allow you to take the NDVI across 1 year, select one point, scroll through all the images, find the maximum NDVI, meaning the image which has the maximum NDVI value in the point that you want to study, and extract it. And this thing is like you can see here. I mean, it is around 50 lines of code. If everyone here have ever tried to do this without Google Earth Engine, this would have meant downloading on your computer around 500 or 600 images. Because of course you cannot know the cloud cover percentage before downloading them. So you have to consider that 463, they are the ones that are without cloud. So the ones that you have to download to check the cloud cover are actually more. Then finally, just going to finish very quick, this is just an instruction to create a palette. So it means that we are creating a vector or like a variable which has inside different colors. And these different colors are a color ramp, like the one that you have in GIS. And then here you basically ask the system to print the NDVI, okay, the NDVI mean on the map, following the palette. What does this mean? It means that you remember that first we select for each point the maximum value. Now we are doing another thing. So we are asking the system, just show another thing. So you can even shut down the polygon. So for instance, if I don't want to see the red square, I just need to click here. Okay, and what did I do here? Here I basically ask the system to print on the map the mean of the NDVI value in each point. So this is no longer the maximum for the 3 points that I selected, but it's just the printing of all the pixels that I have in my study area, and the value in each pixel is the average of all the NDVI values throughout the year. So you can do also, this is nice output, and you see that the colors are basically based on the palette. How does this work? If I remove one color, okay, you will see that the map changed a little bit because I changed the color. Yeah, basically it needs some time because it has to recalculate again map and change the cost. And now let's go finally to the real information. So let's do now what was the objective. So what you can do on Google Earth Engine is to create charts with the calculation that you made. So here what I am doing, I'm creating a chart that is called NDVI field age, meaning NDVI I, that is a chart that select the S2 underscore TS time series. So the time series that we have created that has also the NDVI. We select the point buffer, okay? And we are saying, okay, you have this buffer, so you have to give me back in the chart the average of NDVI within the buffer. This is why here we say reducer. So we want that our system reduce all the value that it finds in the buffer to one number. And now you reduce this value with the average. So let's say that in the buffer we have 4 pixels. These are 4 numbers. This means that we are making the average of these 4 numbers, and the NDVI that we get for that image, for that date in time, for the pixel, or for the buffer that we are studying, is the average. Is that clear? Then we tell them to select the ND normalized difference band. So every time you make one plot, and probably you know that if we are working with satellite images, every image has many bands of wavelength and also has the bands of values that we calculate. So we have to select the NDVI band. And then, I mean, you can also give some information about the system time start and system index. So here you are just saying use the time of the image collection. Because we are working on one image collection. The image collection started at the beginning of 2019 and then at the end of 2019. So with this default instruction, it will print all, but you can also tell him, so the image collection is this long, take half. To start, for instance, the 1st of May, but we are not interested. Okay, and then here you have some instruction about the colors, the labels, and so on. So what do we see in the end? So we see for each buffer a graph. So this is the buffer. This is the buffer for the high resolution NDVI. Okay, this is the medium production NDVI, and this is the low NDVI. But the most interesting thing, in my opinion, is that, of course, with this button, you can have the image, you can download the image, but what you can do, you can also download the data. And then you have all your data on Excel. And maybe you can even make better graphs. Huh? Like you know that if you have like this is very easy to put the data in columns. Okay, just you tell them there is a comma. So here you have all the values of your NVDI. This is very powerful because now we did it for 1 year of Sentinel images. But you can do this with 40 years of Landsat images. So this means that this tool is quite powerful also for getting data that you can manage on your own lab. And basically this is the use that I'm doing. So I'm working with modern management. And I'm not interested in images. I'm interested on maybe how much it was the soil moisture in 1 point of one calculated area for 10 years. So I don't need an information with raster, just need a good time series on an Excel table. And I can do this with cooler images. So just one final notification. So I'm going back here to the old version. So just one final notification. You see here that there are some strange values. Okay, you have some outliers. I mean, that can be explained properly if you consider the filter. So if you filter 10, you will see that these outliers, they will go away. Of course, you will have less images then. You don't see any more than very bad hole in your graph. Okay, so there's a little bit how we work with this, and you see that basically changing one number on the code can give you quite quick overview of how your code can change and quite fast way. I mean, again, I really think that the use of Google Earth Engine should be seen as a twofold application. It's not only useful to map an area, but it's also very, very, very useful for calculating time series. And in this sense, I think the Earth Engine is more revolutionary for the time series rather than for calculating like the change between two images. Because for calculating the change between two images, okay, you save time, but you just need to download two images. But for doing a time series, you will need to calculate 500 images. And this, if I have the code ready, I do it in 10 seconds. So, I mean, there is quite a large trade-off. So just to finish, I mean, these are the other graphs. Of course, I show you only one graph. You will have to do 3 or try to do 3. And this is a little bit of contacts. So the contacts of the project, and Laura and Camilla are working in the project. We have a water harvesting laboratory. We work with the use of rainwater for crop production. And maybe you have the presentation. So if you want to Google or look for us, you will find some use of Google Earth Engine that we did also for, I mean, microclimate analysis or whatever. So I don't know if you have any questions. So just one short thing. Sorry?
I will move ahead.
Yeah.
Yes. So basically, considering we are 2 hours, okay, for the conference, it's not for rushing. Let me also talk to the because what you've done with Valerio Franchi and Giulio Rastelli is already understanding on how to use the code that you will use in the project while check the instructions. Since some of you may have some knowledge of programming and others not, or maybe many not, the idea of the training, also the experience we have in these years in getting you to use code to map, is that at the end of the story, after these 3 lectures, also programming on the first thematic, other change will give you another hands-on, is that you're going to use the code that, as you see, will run, because it's really ready to run. And these 3 lectures is for you to understand the functions, parameters, and the tutors will help you to change them. The system is so powerful and effective that you change the area, it's going to give you the information. But these, almost 2 hours of introduction, and ask questions if it's not the case, from the theoretical introduction by Professor Castelli to this, will give you, enough for understanding when you press run, what the system is doing, okay? So ask questions, directions. Antonio will take hopefully less time, like 15 minutes, Antonio.
I will be short.
Because after the first introduction by Saverio and also Giulio, I think you had enough. I hope so. Okay. And we don't pretend that you to become a JavaScript programmer from understanding, but as a potential data scientist, engineer or geoscience, whatever you are, to understand the functions and plot it. Okay. And don't be scared, because then in the work of the teams, you will have someone of us helping you. Okay. Antonio,
okay, thank you very much. I'm Antonio Annis. Hello, everyone. I'm a research fellow at the Warren Center at the University of Perugia. And now I will show you another exercise that is related to flood detection. So we will use some satellite images in order to get the extension of a flood. Specifically, we will be the flood of Mozambique in 2019. Why doing this? Because, for example, one wants to assess, make a damage assessment. So calculate how many people are affected by floods, or how many crops are affected by floods. So you can also calculate, for example, the tons of crops that are lost and so on. This kind of exercise are like calculation are done, for example, by Red Cross or Water Food Program in order to assess the damage in mostly in developing countries when we have floods like this. In the shared folder we shared yesterday, you can find also a tutorial with all the 3 exercises. So you have the introduction done by Saverio, then forest change detection, and then water change floods. So what we will see now, and the land change. So let's go. So now you see that we have an introduction, and then we have the different codes, blocks of codes that we will see now. And let's do a spoiler. At the end, we will get something like this. So the extension of the floods. So let's start. Let's go to the water detection code. Okay. So basically, first of all, we want to select the study area. So we know that in 2019 there was a flood in Mozambique. So let's go to the Mozambique, the map. And we know that the affected area was in close to Beira. So we can start selecting an area as Giulio showed you yesterday. So you can use, for example, a rectangle, and you can see that you can create a rectangle. And automatically you will have a geometry here. So in order to make a flood detection calculation, you can use both multi-spectral images, so the images you see before. So you can play with the bands of the satellite images. For example, water is very sensitive to near infrared, to green, and to shortwave infrared. So for example, there are some indexes that play with these bands to give you the water extension. But there is a problem because multispectral images are sensitive to clouds, and usually when we have sludge, we have clouds. And also, they are sensitive to lights. So if the sludge occurs during the night, you could not be able to get the extension. So usually it's better to use SAR images, synthetic aperture data. So these are not passive, so they don't get the light of the sun, but they shot the waves, and then they get the waves back. And analyzing the frequency of the waves we are able to get different information, and for example, get information about the sludge. So we will make a change detection comparing the satellite images, the SAR images, after and before a sludge. And then looking at the change between the two images, we will be able to get the flood extension. So the second part of the code is select the time frame. So we know that the floods occurred after the 10th of March. So we get 4 variables: the start, the end, before the flood, and after start and after end. So after the flood. So we will collect all the images between these 2 dates to get a mosaic of images before the flood. Then we will collect all the images between these 2 time frames in order to collect all the images after the flood. And then we will divide the 2 images in order to get the difference. So we will have to set a threshold that allows us to give an idea of how much the images is changed. Of course, if you have a surface of water, then the way the waves go back to the satellite are different. So if we compare the 2 images in which we have bare soil or vegetation and after we have water, then we will get these differences. So after selecting the time frame, you have to select the sensors parameters. So now we will use the Sentinel-1 products, specifically the Sentinel-1 ground detection. That is a product that is already elaborated, for example, with atmosphere correction and so on. We will not get into the detail because we don't have time. I want to leave you more space to do your project. Then you have to choose the polarization. Basically, is the way the sensors send the waves to the Earth and then receive. For this type of analysis, usually we use a vertical orientation to send the waves in the Earth, and then a horizontal orientation to get the waves back. And then you have to choose the path direction. It can be ascending, it can be descending, depends on how the satellites go to our zone. There are some zones in the Earth that are interested only on the descending part, other sites only ascending, and other parts both ascending and descending. Mozambique has both, but in this case we will use the descending path direction. So now that we set these 2 parameters, we can collect the Sentinel-1 images with these parameters. So this is the code. Basically, you have to select the satellite product. We saw the Copernicus Sentinel-1 ground detection. Then the instrumentation mode, interferometric way. This is not important now, but you have to know that there are different ways of acquiring images. Then the polarization, the path direction, and the resolution. The resolution is already set because the Sentinel-1 GRD images are 10 meters resolution. So we are taking the maximum resolution available. AOE is the area of interest, and basically the geometry we created before was named as area of interest. So in this case, we make a filter, a spatial filter, taking only the parts around the area of interest, and then okay, polarization. So now that we have selected the images, we can filter the dates. So we have we see before that we selected the start and before end, after start, after end. So we can filter these images between these two time frames. So we will have two collections: the before collection, which will give the collection of the images before the floods, and after collection. And then we will mosaic these images and click these images according to our area of interest. Now we have to make some calculation. First, there's a smoothing of the images because Sentinel-1 images are affected by some spectral. They call it salt and pepper. So there are some, let's say, spikes in the images that can be have to be smoothed. So you have to choose a smooth radius, for example, 50. And so in this radius, we will make a mean of the values of the images in order to smooth the images. In the tutorial, you will see also which is the effect of the smoothing. So in the left, you have the images before the smoothing, and in the right, after the smoothing. Then we make the flood detection, and basically we just make a division between these two images, the before and the after. In this way, after filtered dot divide before filtered. Then we set a threshold, and we say the threshold is 1.25. So we say if the images before and after changes more than 25%, let's consider this as water. Okay. So then we set the filtered images as with different binary name. So is the difference greater than the threshold? So now we have to refine the results. There are 3 steps for refining the results. One is to exclude the permanent water. So we don't want to have in our images the permanent bodies, the rivers, then the water in the sea, and so on. So in this part of the code, we select the global surface water dataset. This is a global dataset of permanent bodies that stays full of water for more than 10 months. And then we just mask our results using this data set. Then we compute only the connectivity pixels. So we exclude all the pixels that are not connected to the main slabs. To understand better, maybe it's better to visualize what I'm saying. Here you can see that there are a lot of alone pixel not connected. And after this operation, we exclude this pixel and we get only the larger area. Okay, so it's just a cleaning of our images. And this is the code. Finally, we eliminate, so this was the code for the connection. And finally, we eliminated the hill slope area. So the areas with a slope greater than 5%, because in the hill slope area, we don't have the flat plains. So we exclude all the areas that probably are not affected by floods because there are slopes. So this is another filter. We get this digital elevation model, so a model that gives you in each cell the elevation. Then we calculate the slope this way. And then after we have the slope, we can exclude the area which is sloper higher than 5%. Finally, you can plot the results. So basically, you can center your map at your area of interest. So for example, if you are in another zone, no. If you are in another zone, then you run the code, you will be moved to the Mozambique. You will see the after filtered mosaic images, the before filtered images, the difference between the two images, and then the flooded area. So the one obtained with the difference and then the refinement. Let's run the code to see. Okay. Okay, this is the results. So as you can see, the blue polygon is the one which we get the flood extension. If you are curious to know how to proceed, I have a link with like a more extended tutorial in which you can do other calculations. For example, calculate the flooded area or calculate the number of people that are affected by the floods, because we have data set of population cell by cell. And then you can also estimate which kind of land is affected and also the crops that are affected. This is the link. This is a link to the United Nations portal. Let's go briefly. No. Here, there is a tutorial that is very similar to the one that I saw you, just a little bit longer. And there is also the link to the entire code. That is this one. It's very, no, I have to change the, okay, this one. No. Sorry. Bad request. Okay, this is the link. So you will find a very well organized code in which there are different blocks, for example, data selection, flood extent calculation, then damage assessment. And so you get a population data set, then affected agricultural land, and so on. And then display the products, and you can also produce maps. For example, if I ran the code, now the code now is not running, I don't know why. Yes, because I have to select the geometry, that is this one. And here you have also like an interface in which you will see number of hectares of croplands that are affected, number of urban areas that are affected, and then here you have the legend with all the layers that are produced. For example, if you want to study another area, you can search for flood events occurred during the world in the last years. And I also share with you a database of flood events from the UN portal, this portal here, in which you can find a database of occurred floods and also the extension of occurred floods in different parts of the world. For example, let's type Kenya. There was a flood in the 4th of May 2018. So if you, for example, want to make the same calculation in Kenya, you can get the Sentinel-1 images after and before the 4 May 2018 and make a similar analysis. Do you have questions? Also, from the online participants, there is some questions about it.
No, thank you. Everything okay.
Okay. Sorry? The one is the map of the day in which the images of the flood has been detected. So if you want to make a change detection exercise, you have to take a date before the 4 May and a day after or immediately.
How to change the date?
Sorry?
How to change the date?
No, this is, you have to go to your code, you select Kenya, and then you get the data before this, the 4th of May, and after the 4th of May, and make a change of detection and see if something is get by the satellite. I suppose so, because they get it. Okay. Yes. Yes, now we can start with your own project. So basically you have to choose which theme you prefer, change detection, forest, land change, floods, and then you can do a script very similar. For example, in another area of the world, or if you get passionate about this environment, you can also completely change the code and do different things. You have to know that online there are a lot of tutorials of Google Earth and a lot of also exchange of opinions between the coders. So you can find a community of Google Earth engine, and there are a lot of people that every day ask, I can get this error, how can I solve this? And there are a lot of supporters that help people to improve the codes and to solve the problems. So basically, you can, how does it work with the COVID situation? We can do groups?
Yes, let's do before the coffee break. So I will give you 5 minutes break. 7. That's the time to go to the coffee machine and come back. Now, we'll do a break, but before the break, we organize the groups. We don't know you, and we need to just ask you to bring up students in the same class to 4 groups that we want to work together. You can also work all single, but we would like to have groups because it's easier for us to follow you rather than 20 single projects. As you know from the program, there are 3 thematic areas. So after you form the groups, I would suggest groups of 3-4 people maximum. 2 is not enough, 3 I think is perfect, 4 is maximum, I would advise. And then you, in the group, you identify the area you like, water, land, forest. So that the tutors will be Antonio, water floods, Judith land, right? Hmm? Yes, into land and some area forest, right? Okay. And the others will follow. I'm not the other 3, but the others also do equal. How do you select then the project? From very simple, like from the case of Antonio, that also give you the suggestion that you have the UNOSAT flood maps from other, from the agencies. So you select the recent flood in Oman or the other one in Congo. You go in the area, you already have the tool that works. So to make the story short, in 5 minutes, because the code is already running, you have the slide, the image of the observation already prepared. You have your code running the image. You put these 2 images in 2 slides. You show you understood what you did. Finish. So there will be 10 minutes, or maybe a little more. But you have almost 2 hours. Consider that the slides you will do in the afternoon. So the presentation you put together in the afternoon. So you have more than an hour, almost 2 hours to identify the project, do the mapping, and with us supporting, finalize this exercise. The more you go into the code, because you will see that you have parameters, the more you learn. So these tutorials will help you in understanding the code and make some changes. Okay?
Maybe the study area.
Yeah,
the study area that you know.
There are the experts in the thematic areas, but generally, land and forest change. Even Googling, you will find something interesting. I remember, probably still on, there is a Google site with the time lapse, right? That is still on. If you don't know where to go, there is a Google time lapse. Is actually in the front page. Originally, was the front page Earth Engine platform. You will find those tools like the one that Saverio showed about the Sentinel, about the panel tool, the one showing the change. So you have plenty of examples in this Earth Engine landing page about changes, Earth changes. Okay, so you can get inspired. Okay, coffee break. Come back as soon as possible. Yes.
Also, the online participant can do an exercise if they want.
Yes, we will work alone, I think.
Yes, what about?
Stay 4 on the same computer. By organization, I need to say this. Then you work. The online. Yes.
To the online students, are you listening about the
Yes, we are here.
Yes.
We'd like to posso fare invece cercavo di dirvi se scrivono richiesta di aiuto.
Una specie, autistica Asperger. È una forma di autismo. Eh sì, mi fa che me lo voglio far attenzione. Ma così. Vabbè, comunque, è una forma di autismo. No, hai visto come ti ha risposto? Cioè, praticamente manca tutto, cioè, non so quanti crediti, ma quanti crediti è? 9 o 6. Vabbè, però non si può fare dal 9 un corso di riconoscimento solo 4, quindi niente. E poi ora ti ha scritto anche Marino e dice che manca una...
ሲገባ አሁን ለትልቆች ለትንሾች ቦታ ቢለቁላቸው ምናምን እያለች ነበር። ናፎሚያ የሀዋል ልጅ ምናምን እየበረቃቀፋቸው ሲገቡ እንትን እያለች ነው። ተራ ሁሉም ቀስ ብሎ የሚገቡ ነበር። ተራው ጥሩ ነበር። አሁን በቃ ናፎሚ ገቡ። የሀዋል ልጅ እንደውም ይበሳል ገቡ ነው የሚያደርጉት።
እንደዚህ